For today, what causes the second high tide we experience every day? You may not be sailors, but it is a fact that every day there are approximately every 25 hours, there are two high tides down at the Virginia beaches. And the question is, what causes the second one? Because after all, I guess we feel comfortable with the fact that the moon is pulling up the water, that the moon exerts a gravitational force on the earth, and that pulls up a lump of water, and that's a high tide. This was not Galileo's understanding, but Newton has given us this. When Newton introduced us to gravity, he also thought that this could be explanation of the tides. But we do have this other tide here on the other side. That every day we turn once around on the earth and we pass through this high tide under the moon, but we also pass through a high tide that is on the opposite side of the earth from the moon. What is causing this high tide? And you have a very nice set of multiple choice questions to choose from. And if you're very anxious, you just wait a minute and I'll tell you the answer, and then you can put that down. The answer is that there is a great race taking place, that we in our Aristotelian narrowness have a very hard time dealing with an earth which is moving. We also have a hard time dealing with other things pulling on the earth. We think gravity is what earth does, and we're very comfortable with the earth pulling on the moon and the moon pulling on the water, but the fact is that the moon also pulls the earth. And so the gravitational force from the moon acting on all these parts of the earth is going to be strongest on the near side, because gravitational force varies inversely as the square of the distance. The gravitational force on the earth is going to be weaker than the gravitational force on the near side of the earth, and the gravitational force on the far side of the earth is going to be the weakest of all, because it is the furthest away from the moon. Each of these forces causes acceleration. So the near side of the earth itself, and the far side of the earth are all accelerating towards the moon, but the near side is going to accelerate the fastest, and so it gets ahead of the earth. But the earth accelerates faster than the water on the far side, and so the water on the far side gets left behind. That is the cause of this bump on the other side. It's that everybody's accelerating towards the moon, but this water is not accelerating towards the moon as fast as the earth is, and it gets left behind. Tides are not something that happen in water. They are something that happen in anything that experiences variable amounts of gravitational force. The earth itself is plastic, and the pull on this part of the earth is greater than the pull on this part of the earth, is greater than the pull on this part of the earth. Earth itself, not just water, but earth itself gets pulled out into lumps by that varying strength pull. And so there is a tidal bulge that is in the earth. In fact, when the moon goes across Richmond, we rise in the air, I believe, about half a meter. That relative acceleration causes the part of the earth that we're on to move away from the center of the earth by about a half a meter. That's pretty awesome. But wait, there is more. It turns out that the moon is not overhead when you are in a high tide. That in fact, you, as the earth turns, and here's a remarkable thing. Here's the earth going around the sun. Here's the moon going around the earth. Here is the Earth spinning, and here is the moon spinning, and all of those are going in the same direction. How lucky was that? It's not lucky at all. Well, why, Mr. Houghton? For the answer to this and other questions of great fascination, you need to sign up for astronomy. But the fact is that although the moon's gravitational pull is pulling up this lump, the lump is not under the moon. It's, I forget how much, maybe as much as a half an hour after we pass under the moon that we go through this lump. So how is that? And I think you're supposed to give an answer on the worksheet. Maybe not. The answer is that the Earth spinning exerts a frictional push on this water, and when that lump gets there, the spinning Earth's friction pushes the lump ahead of the moon. So that's why the lumps don't line up, because they get pushed ahead by the spinning Earth. But wait, there is more. The moon also feels varying pulls from the Earth. The near side of the moon feels greater pull than the far side of the moon from the Earth. And so the moon also, although it has no water, ends up with lumps, and it has tidal bulges. And these would then not line up. And so there is a gravitational force that pulls this lump on the moon forward. Towards the lump on the Earth, and that would tend to retard the spinning of the moon. And similarly, this lump on the Earth is pulled back by the moon, which would tend to retard the spinning of the Earth and slows the Earth down. The result of this pull from the moon very quickly in the moon's existence slowed it down, slowed this rate of spin down such that the lump is always pointing at the Earth. It's always in the same location. The moon continues to spin, but now it spins at a rate such that this lump is always pointing at the Earth. Which means the moon has slowed down so much. Well, I think you're supposed to answer this question. What would that mean if the rate at which the moon turned is identical to the rate at which it orbits the Earth? Good, I'll leave it. I won't answer that question. The Earth is also being slowed down. Something like 600,000 or million years ago, the Earth had a year that was about 400 days long. We can look at growth records in coral, that each day the coral grows, and just like tree rings, you can see how much it grew each day, and thus know how many days there were. And it used to be that days were something on the order of 22 hours long, and the Earth took about 400 of them, 400 spins as it went around the sun once in a year. That is, the day was shorter. But this pull from the moon has been slowing the Earth down, and now instead of 400 days in a year, they're 365 and a quarter. And it continues to slow the moon down by something like seconds on the century, something like that. It's a very slow that it's slowing it down, but it is happening. You come back far enough in the future and you will find that there are even fewer days in the year than there are now. Okay, shifting gears. Are astronauts orbiting in the space shuttle weightless? And in answering that question, which I would like you to answer, I would like you to consider what it means to be weightless. What is our definition of weight? And if, whoops, come on now. If this astronaut going around the Earth, we'll put him in the space shuttle, although that doesn't exist up there anymore, but in this space station, we're going around the Earth. If there were no weight, no pull of Earth's gravity on that person, what path would they follow? And I think you can see that this is not what the astronauts do. They do not, here we draw it, they do not leave Earth orbit. So clearly they are not weightless. Now, NASA seems to have tried to fix this misnomer. You see, the people inside the space shuttle don't fall. That they float around in the space shuttle. If you have a pen and you hold it out in the air and let go of it, it just stays there in the air. It doesn't fall. It looks just like weightlessness. But it's not. And, oops, aren't you going to go away? Here, oh, heavens. Okay, we'll just leave that arrow there. No, we won't. Come on now. There we go. I'll get rid of this too. That they're not weightless. NASA sometimes calls it microgravity. That they're in microgravity. That is a horrible mistake that they are making. They've never asked my opinion about it. But in fact, if the acceleration due to gravity, the strength of the gravitational field at the Earth's surface is 9.8, up where the space shuttle goes around, I believe it is something like 8.6. That is hardly micro. It is less gravitational force than here, but it's not less weight that they have. They are weightless, or they appear to be. How does that happen? Well, consider this. We have a classroom in an elevator. Here's the cord holding the elevator up. And into this classroom steps a physics magician with his top hat. But rather than pulling a rabbit out, he holds out an apple. And he says the magic words, and when he says, "Hey presto," his assistant cuts the cable, causing the elevator to fall. The elevator will be in free fall. The elevator will accelerate downwards at 9.8. The magician will accelerate downwards at 9.8. The apple will accelerate downwards at 9.8. This little girl will accelerate downwards at 9.8. Everything is accelerating downwards at 9.8, so when does the apple catch up with the floor? And the answer is it never does. Because you are in a frame of reference which is accelerating, you make up bad physics to explain what is going on. That you say that the magician has created a magical force that holds the apple up against gravity. But in fact, the apple is accelerating downwards, but just as fast as the reference frame. You create what is known as a pseudo-force, a false force. And the reason you do is because you are in an accelerating frame of reference. Indeed, when they want to train astronauts for the experience of being up here, quote-unquote, weightless, what they do is they take them up in an airplane and they take the airplane up in the air and then cut the cable. They just let the airplane drop. And the experience that they have inside that airplane is exactly identical to the experience you have in your spaceship orbiting the Earth. You are constantly accelerating towards the center of the Earth at exactly the same rate as your environment is. And therefore you do not accelerate relative to your environment. It feels like weightlessness. And it looks like weightlessness. Here's another pseudo-force You're traveling around a curve. When you travel around a curve, you are again in an accelerating frame of reference. You could tell me, accelerating how? And as a result, you invent a force called centrifugal force to explain the behavior of things. That if you are riding on this curve and your car has a star sitting on the seat, let's get it out here. Yes. The star is going to inertially travel in a straight line. But the frame of reference, that didn't work out so well. The frame of reference is moving along the curve, and so the appearance is that something has pushed the star, to the outside of the car. We call it centrifugal force. But in fact, it is that the car has accelerated inward and the star has not. And yet we invent this force that doesn't exist to explain what is going on, because we are in an accelerating, also known as a non-inertial frame of reference. Shifting gears only slightly, we have a car with a watermelon in the trunk. And here's another car with a watermelon in the trunk. This car here suddenly accelerates forwards. What's going to happen to the watermelon? This car here, however, does not accelerate forwards, but instead what happens is it goes up a hill. What's going to happen to the watermelon? This illustrates two different qualities of mass. In this case, we would say it is inertial mass that is causing the watermelon to seem to move to the back of the trunk, although that's just because we're in an accelerating frame of reference. In this case, it is called gravitational mass because we are in a gravitational field and the car is at a tilt, that the watermelon moves to the back of the truck. And it was a great concern to physicists whether these are the same thing or not. Is inertial mass the same thing as gravitational mass? And they worried and worried about that. Ultimately, Albert Einstein said in his famous principle of equivalence that they are the same thing. Indeed, Einstein suggested that if you were in a rocket that was accelerating upwards, there is no way, there's nothing you could do to distinguish from what went on inside of that rocket accelerating upwards from the same environment in a gravitational field. That everything in this classroom in the Earth's gravitational field would behave identically to everything in this classroom in an accelerating frame of reference. There is nothing you could do to distinguish between the two. That's Einstein's principle of equivalence. He goes on to use this idea to explain that, in fact, gravity, this whole notion of gravitational mass, doesn't really exist. That gravity is not a force. Gravity is a pseudo-force that we talk about because it is our experience in an accelerating frame of reference. That what Einstein said was that mass causes a deformation in the space-time fabric, and to move close to this large mass is to move through that deformed fabric, and inertially you are going to be accelerated because of the moving through deformed space, and as a consequence you say, oh, well, if I'm accelerated, there must have been a force that caused the acceleration, and you invent gravity. But in fact, gravity is just an inertial effect created by the deformation of space-time by masses. This illustrates the famous, I think it was 1919, that they decided to test Einstein's general theory of relativity by looking for this deformation of space. There was going to be a total eclipse. They had to go down off the coast of Africa to see it out in the ocean, and then there was trouble with the weather. But they feel like they got enough data that they looked The moon was blocking the sun's bright light, so they could see right next to the moon a star whose light was bent. It was bent because of the gravitational field of the sun, which pulled on the mass of the star, but in addition to that, it was bent because of the deformation of space, and it was bent just the right amount, and everybody got banner headlines in the newspaper that this was the confirmation that Einstein was correct with his general relativity. Okay, totally shifting gears. We've been talking about the force of gravity and then dissing it, but force causes acceleration, and there are a very limited number of forces in nature, and I would like you to parrot them to me. You think about accelerations that happen. What is the force that causes them? And I hope gravity would occur to you as one of these fundamental sources of acceleration. Perhaps less easily, you would think that electricity, you can make the hairs stand up on the back of your hand, you can make little pieces of paper jump around. That is an acceleration. That would be electrical, is another fundamental force. Magnetism, you can make paper clips accelerate. So there you are. There are two more, and they would probably not be so obvious to you. One is strong nuclear force. When the physicists figured out that the atom had a nucleus with positive charges in it, they said, whoa, wait a minute, that can't work because positive charges would repel positive charges. How are you going to make a stable nucleus? And so they invented another force called strong nuclear force that holds the nucleus together against the force of electricity, and it's much more complex than that. There is finally a fifth force that is called weak nuclear force, and I cannot tell you what weak nuclear force is, nor evidently can anybody else. That what you will find if you look it up is that it is a force that is involved in some forms of nuclear decay, which for me tells me nothing about it. But the physicists feel very strongly that it needs to exist, and so this list of 5 I would like you to give me. In the middle of the 19th century, a guy named Faraday discovered the sense in which we could use electricity to create magnetism. And with that, the list fell to 4. Electricity and magnetism became just one force called electromagnetic. In the 1970s, they collided particles together with sufficient energy that they saw the bosons, which are the transporters of weak nuclear force, and they behaved exactly as they thought they should, and this then lowers the list to 3, that electromagnetic got combined with weak nuclear. All of these forces behave very similarly, and physicists really believe that ultimately this could be reduced to just one, and that's called unified field theory. That there is just one fundamental force, that these are just different idiosyncrasies of that force. That if you were to give the physicists enough money, they would build a particle collider that was sufficiently powerful that they would find the unity between strong nuclear and electroweak. And if you gave them enough energy to create the Big Bang, they might be able to unify it with gravity. Don't give them that much money. It would be rather harsh effects on the Earth. So you could give me a list of 3, or a list of 4, or a list of 5 when I ask you. It has to be the right ones, though, not just any old 3. This would probably be the preferable list for you to give me when the time comes. Thank you, and good night.